So I've got a really nice video for you guys today. It's a collaboration with Tom Crawford from Tom Rocks Maths. Maths, not math. So today I'm going to be teaching him a little bit about Lie algebras, and then a video on his channel, he's going to teach me a little about the Heisenberg uncertainty principle coming from a mathematical standpoint. So let's get going.
Hello everyone, real pleasure to be joining Michael here today. So I am a mathematician over in the University of Oxford, a long way away, but I'm really excited to be exchanging ideas and doing some maths over on Michael's channel.
Okay, great. So let's get into it. So I want to start with like a fairly simple definition, and that's the definition of something called an algebra. So an algebra starts with a vector space and then endows it with a multiplication. So to be more specific, an algebra, so I'll call it A, is a vector space. So over a field, but we can take the field to be the complex numbers or the real numbers. But in general, for the study of Lie algebras, at least the first time you go through the study of Lie algebras, you want to work over the complex numbers because they're like the simplest field to think about that's algebraically closed. Okay, so it's a vector space over C, whereas of course you could like think about some sort of completion of a finite field, which is algebraically closed, but that makes things a lot more complicated. So we'll just go over C. Okay, so an algebra is a vector space over C with a multiplication. So I'll just say a multiplication. We'll maybe call it star, although depending on the setting, we'll use a different symbol that's like sort of more obvious to the example that we're working in. Okay, so we've got this multiplication star, which has two inputs, each from A, and gives you an output from A. And so just to like say this really quickly, what you want star to be is like a bilinear map. Or maybe thought about otherwise, left multiplication by any element and right multiplication by any element should be a linear transformation in the vector space. So we can write that down like semi-carefully by saying maybe we'll use alpha, beta, and gamma to come from the vector space, in other words, the algebra A, and then let's say we have some sort of complex numbers, C1 and C2. So those are complex numbers. So here we have our vectors. So we're going to talk about multiplying these vectors with this star operation, and then we have our scalars here. So given the fact that the algebra is already a vector space, we have a lot of like nice endowed structure with the addition of the vectors and the scalar multiplication of the scalars. And so what we really need to do is just like see how the scalar multiplication and the vector addition behaves with respect to our new operation. And I mean, the thing is it behaves like the way that you would want it to. I mean, which is just like kind of a standard mathematical thing. You know, everything should work the way that it does for numbers, or maybe as it does with numbers with like slight tweaks to make it a little bit more general. So we would want something like this. So if we take a complex number and multiply it into the product of two of our vectors, so this is the scalar multiple of A star or alpha star beta. So recall that alpha star beta is going to be an element from A because we've got this operation. This is the same thing as doing the scalar multiple with any of our vectors and then doing our algebra product. So here we've got alpha star C1 beta. So that would be one thing. And then maybe we've also got like a distributive rule. So we've got alpha, maybe let's make sure to put a star here, and then beta plus gamma is equal to alpha star beta plus alpha star gamma. And then maybe we would have another distributive rule based on this one, but it would be like a right distributive rule. And I'd like to point out here that there are some characteristics here that are missing, and that would be associativity and commutativity. And those are missing because for the kind of strict or simplest definition of an algebra that doesn't have any additional structure, we don't require commutativity or associativity. Okay, so that being said, what we can do is look at a bunch of examples, maybe starting with some examples where we do have this additional nice structure, and then moving to examples where we don't have this initial nice structure. So maybe like the simplest example would be just the complex numbers themselves. So that's a field, right? So maybe we would say A is just the complex numbers. So any field is like a vector space over itself. So we know that. And then what's the multiplication? It's just multiplication of complex numbers. So notice this actually inherits like a lot more structure. So this definitely includes all of this stuff, but it's also associative, it's also commutative, and also we have like inverses all over the place, right? So like, I mean, essentially everything is invertible except for the zero vector, which is just the zero complex number. So this isn't like super interesting, but maybe we could like push this up a little bit and make it a little more interesting by looking at maybe the classic example of a commutative and associative algebra, and that would be the complex numbers, or sorry, the polynomials, where complex numbers are the coefficients. So these are polynomials in variable x, and then coefficients are complex numbers. And so some examples of things in here would be like 2 plus x plus 3x squared. If you want to like really point out that there's a complex number in there, you could have like 2 plus I times x cubed, etc. So those are like examples of elements in, well, I would say this is like C adjoin x or the polynomial algebra x. And so like in an abstract algebra class, you would learn about something like this. It would be like a polynomial ring or something. And maybe at the end of a first semester abstract algebra class, you would study a lot of things about K adjoin X, where K is like an arbitrary field. You wouldn't really say the word algebra for some reason, but you would definitely think about it as like a ring, and you prove that it's like got unique factorization and all sorts of interesting stuff. Okay, so just like this example up here, it has a lot of additional structure. So let's notice that it's definitely associative, it's definitely commutative, but there aren't really any inverses to speak of. The constants have inverses, but none of the other polynomials have inverses. Just think about like taking the reciprocal of a polynomial. To do that carefully, you would probably expand it as a power series, but then it's no longer like a finite linear combination of things, so it's no longer a polynomial. Okay, so now let's move up and see if we can come up with some simple-ish examples where we discard some of these properties. So maybe the one that would be like most obvious, which you would learn about in like a linear algebra class, although you might not use these words, would be the algebra of matrices. So I'll just say, we'll say M 2 by 2 to mean all 2 by 2 matrices, although like you could also have N by N matrices, or if you want to be like super fancy pants, you could say something like all linear transformations from a vector space to itself. So just to be like really thorough here, this would be like A, B, C, D, where A, B, and C, and D come from, in this case, we're using complex numbers, but like I said, it could be anything like real numbers, rational numbers, whatever. So from linear algebra class, we know that this I should say, what's the multiplication? Well, it's going to be multiplication of matrices. And so from linear algebra class, we know that multiplication of matrices is associative, but it is not commutative. So we could put like commutative there and then just put an X to it. So it's not commutative. So we've lost one of our structural elements that we have in our previous two examples. Okay, cool. And I would say that these are all pretty like digestible examples. And so the next question might be, can we get rid of this associativity and still have a digestible example. And we can, and it would be something you would learn about in maybe like a multivariable calculus class in the US.
I teach multivariable calculus, or it's sometimes called vector calculus as well, possibly.
Yeah. So you could tell me if you would like see that where you would see this for the first time. So I'm gonna just like, since we've been working over complex numbers, I'm gonna use complex numbers as our base field still, although like in a standard multivariable calculus class, you would use real numbers. So let's use the 3-entry complex numbers. So we've got A, B, C, where A, B, and C are complex numbers. And then our operation is the cross product. So here I'll write my multiplication is equal to the cross product. So if you recall the cross product in real numbers, it takes in any two vectors and gives you a vector which is orthogonal to those vectors. So you can just do the same sort of algebraic manipulation on complex entry vectors and get the same kind of thing. So now this is no longer associative either. And generally, in a multivariable calculus class or wherever you see the cross product for the first time, an exercise or an example in class is generally given to show that we do not have associativity here. And it's pretty easy to cook one up just with like unit basis vectors. So for example, if you take like I cross J cross, let's see, J, you'll definitely get the 0 vector, right? Because we know J cross J is the 0 vector. Versus if we do I cross J cross K, we will not get the 0 vector. So I cross J is, oh no, sorry, I cross J, right? We want them to be the same, but we've just changed the associativity, right? Well, so I cross J is K, K cross J is I. So here we've got an example that's pretty simple, just with unit basis vectors, and maybe like one of the first things you learn is how the unit basis vectors behave under this cross product, where we see that there is a lack of associativity. And so you might say, well, okay, there's a lack of associativity, but is there like some sort of other close to associativity structure? And there is. But that requires us to look at another definition. And maybe while I'm erasing this, I would ask you, where's the first place you learn about the cross product in the UK?
I think in the Oxford course we do it in geometry. So in the first term we have a course in geometry which kind of takes everything you've learned at high school about Euclidean geometry and circle theorems, triangle theorems, and then just translates all of that into vectors. So you're proving the same results like Pythagoras' theorem, but you're now using vectors. And so it kind of naturally leads to definitions of dot products and cross products, as you mentioned yourself, about the idea of the cross product between two vectors gives you something orthogonal to those two vectors.
Right.
So I'd probably say geometry, and then we follow it up with multivariable calculus or vector calculus as well.
That's really nice. I feel like, so in the US, I think most students would see it for the first time if they took a physics class, like a first semester physics class. But if someone never took a physics class, I think they may not see it at all until multivariable calculus.
Right. Mm-hmm.
Which is like kind of a bummer. Although, you know, it's not like the be-all, end-all operation, but yeah. Okay, so I think we have a pretty good idea what an algebra is, right?
I'm feeling relatively confident. Despite being an applied mathematician, I have followed everything so far.
Okay, sick. Okay, so now let's look at another definition, which is a type of algebra. So I might like say that we could have a definition in between where we define something called an associative algebra. So that would be an algebra where we have the associative property. So most of these examples before were associative algebras. Or we could have an example which was a commutative associative algebra. So that would be, the first two examples were both commutative and associative. But what I want to do is give an example of maybe the simplest type of non-associative algebras. There's like a lot of different types of non-associative algebras, but the one that I'm going to describe is a Lie algebra. And that's because, well, first of all, it's kind of my area of study, but also it has like really important applications in physics. It allows you to study group theory. It's, in fact, we're not going to talk about this, but it can be described as like the linearization of a certain type of group. And it actually generalizes this kind of notion of the cross product that we saw before. All right, so let's say we've got an algebra. L is a Lie algebra. So it's named after Norwegian mathematician Sophus Lie, a student of Silo, of the Silo theorems. Okay, so a Lie algebra with the operation. So instead of writing an operation star, we have a special symbol for the operation for a Lie algebra, and that is this bracket symbol. So operation bracket. So it takes two vectors from the Lie algebra. So let's say it goes from L cross L to L and gives you a new vector from the Lie algebra. And then it satisfies some rules. And, well, it satisfies all the rules of an algebra, so we won't write those down, in addition to two more rules. And those are something called skew symmetry. So skew symmetry says for all, maybe I'll call them alpha and, or maybe, yeah, that's fine. Alpha and beta in L, we have bracket alpha beta is the same thing as negative bracket beta alpha. And then maybe there's like a really nice exercise here, and that would be to show that this is equivalent to, so this is if and only if alpha alpha equals 0 for all alpha in L. So those are two different ways of writing like skew symmetry. Either we kind of have this anti-commutativity, or we have this, which is like maybe more appropriately called just skew symmetry. And this actually doesn't always hold. This holds as long as your field is not characteristic 2, but we're working over the complex numbers, so we're okay there. All right, so that's our first rule. And notice that cross product most definitely satisfies this, right? Like one of the first things you learn about the cross product is that V cross V is equal to 0, right? And I always like describe that to my students in the following way. So, you know, V cross W is supposed to give you a vector that's orthogonal to V and W. But if you do V cross V, there will be infinitely many vectors orthogonal to V, like an entire plane's worth. And so the cross product gets confused. And as the cross product gets confused, it doesn't know what to do, so it gives you the 0 vector. Yeah. I mean, obviously, like there's like some structural stuff going in there, but I think that's like kind of a cute way of remembering that the cross product of a vector with itself gives you 0. Okay, and then you've got one more identity called the Jacobi identity, and that goes like this. That goes like alpha with beta gamma. So check it out what we've got here. We've got like some sort of associativity, right? So if you were to read this off with just normal multiplication, it would look like this, right? Like if we weren't using our bracket multiplication, it would be like combining beta and gamma like that. And then after combining beta and gamma, we're combining alpha from the left. Okay, but that's just using our bracket notation. And then we've got plus, let's see, gamma, alpha, beta. and then plus beta, let's see, gamma alpha equals 0. So this may seem like, it's just sort of crazy out of nowhere, right? But notice each of these brackets has the same structure, right? It has vector, 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 right? And these vectors are cycled through, right? So we start off with alpha, beta, gamma, and then you can think about these going through on like a circle like this. So alpha goes to this position, beta goes to this position, and then gamma circles back to this position. Yeah. And then like we're doing the same thing as we move forward until we've like hit all of these kind of cyclic permutations of the entries here. Okay, so this is skew symmetry, Jacobi identity. Jacobi identity is like important. There is a type of algebra that does not have skew symmetry but does have Jacobi identity, and that's called the Leibniz Algebra. You know, maybe we won't talk about this super carefully, but that's because if you write this carefully, it looks like the product rule from calculus. Yeah. Okay, so let's look at some examples of this. So we'll look at some general examples, and then after looking at general examples, I want to give you maybe like what I think are two of the most important examples, a finite dimensional version and an infinite dimensional example, which I think is going to be related to the talk that you give me. Okay, so here are our examples. So let's take M2 by 2 again. So remember that was like all 2 by 2 matrices, A, B, C, D. A, B, C, D are complex numbers. But now instead of taking our operation to be matrix multiplication, we'll take our operation to be the commutator. So in other words, like AB, so bracket AB will be AB minus BA. Okay, so this in fact forms something called a Lie algebra, and you can check these things pretty quickly. So notice that AB is most definitely negative BA. That's not too hard to see just by like factoring a minus sign out of this. And then maybe we'll expand one of these and then like leave as like a little homework exercise to expand the other ones and then observe that they sum to 0. So if we would do bracket A with bracket BC, that's going to be the same thing as bracket A with BC minus CB, right? That's this bracket. And then we would have A, BC minus ACB. So just to be careful here, this guy right here is A with BC minus CB, right? And then from that, we would subtract BCA plus CBA. And just to be careful here, this will be BC minus CB with A on the right-hand side, where I've like carefully distributed the minus sign. Okay, so that is this type of object. But then if you were to write down the other guys like this over here and sum them up, you would get 0. So this may seem like, oh, well, that can't be all there is to it. But in fact, like, I'm going to put most here. So most Lie algebras, I would say like all finite dimensional Lie algebras, most Lie algebras can be written as subspaces or subalgebras of matrix Lie algebras. So if you understand what's going on with the matrix Lie algebra, it's like actually kind of good enough to understand what's going on with most important ones. Okay, so let's look at maybe another example. And I mean, there was a reason why we did the cross product before, and that's because the cross product has the structure of a Lie algebra as well. So like say we've got C3 and cross product. So here we're taking the commutator of V and W. I shouldn't say commutator because that's not like what it is. The bracket, you know, it sometimes is the commutator. When it's represented with matrices it is, but this is like V cross W. And then, okay, well this most definitely satisfies this rule. So we'll just put this as fact, maybe like homework exercise from when you're learning about the cross product is that when you, when you commute the cross product, you get a minus sign. It's like the right hand rule, right? And then this over here is also like another example of, or another good homework exercise showing that the cross product satisfies this Jacobi identity. I think in most textbooks that I've seen showing that the cross product satisfies the Jacobi identity involves like doing a kind of a problem right before it where you write the cross product as like a linear combination of things with the dot product. Like the triple cross product is some sort of linear combination of objects with the dot product.
Yes, yeah, vector identities, of course. Yes, you have your triple cross product and you simplify it into does it have 4 terms, I want to say, involving dot products and things, I think, yeah.
Yeah, and there's a name for the identity. Did you just say the name?
No, I just call them vector identities. There's a list of like 10 that you just need to know. Yeah.
Oh, yeah. I think...
Yes.
There's a name, like some dude. It's named after some dude. But anyway, yeah, that's the easiest way to do it. Okay, and then, I mean, we'd probably be like, it would be a little problematic if we didn't like give maybe the most universal way to find one. And that would be like, we take any associative algebra. So let's call that A. And so let's say that A has operation star, and we endow it with a new operation, and that operation is bracket, and it does exactly what you think it should. So it does A star, or alpha star beta minus beta star alpha. That's an example. You can endow any associative algebra with the structure of a Lie algebra like this. And then, well, you know, you can actually kind of look at some more stuff going on here, but I think that's good enough to say about that. And maybe we should like now look at 2 of the most important examples. Not that this is an important example, but I would say 2 very, very important examples of Lie algebras, maybe a finite dimensional version and an infinite dimensional version. For our finite dimensional version, we'll look at something called SL2. So it's the special linear Lie algebra. So here we'll say SL2. And what it is, well, technically it's not this, but it can be represented as matrices this way. So we've got A, B, C minus A, where A, B, and C are complex numbers. So maybe in general, because this is a 2x2 case, but in general, there should be some sort of way for doing this for all n, and there is. So SLN will be all n by n matrices. So let's maybe write it like this. A is an n by n matrix where the trace is 0. So that would be an example of the SLN. So notice we've got the trace is equal to 0 here, right? Yeah, because A plus negative A is 0. It's really, really intense stuff happening. Okay, so a nice like linear algebra homework problem. You know, and you can like find out a lot about the professor who's teaching you linear algebra by like the weird homework problems they give you. Like if your multivariable calculus instructor tells you to prove that the cross product does the Jacobi identity, something's going on there. And if your linear algebra instructor tells you to find the basis of this and then like show some stuff, then there's something going on there. So you can calculate the basis of this pretty easily. Well, and in fact, we kind of already did, just given the fact that we've got these three free variables here. So we can extract the basis by just setting one of the free variables equal to 1 and the others equal to 0, one at a time. And that'll give you these following three matrices, or really like vectors, if you will, because, you know, 2 by 2 matrices makes a vector space. Oh, and this is definitely a subspace of the space of 2 by 2 matrices. Well, for a bunch of different reasons. It's the null space of a certain operator. Okay, so this is equal to 0, 1, 0, 0. So we'll call E, that will be that vector. So notice the trace of that is definitely 0. We'll say F is equal to 0, 0, 1, 0. So again, the trace of that is definitely equal to 0. And then H will be the diagonal one. So 1, 0, 0 minus 1. So this, generally, we think about like SL2 as being the span of this E, F, and H. And often, we just think about it as these three symbols like abstracted away from the representation as matrices. But that's kind of neither here nor there. So maybe what we'd really like to do to see the structure of this SL2 would be to see what it looks like if we take products of E with F, E with H, and then so on and so forth, right? That should give us an idea for how this thing behaves. So let's do a couple of these. Notice there aren't that many to do because we have skew symmetry. Well, and trivially the Jacobi identity, but that, you know, doesn't help us out quite as much to reduce the number of calculations to do in this three-dimensional case. So we don't really need to do E with E. We'll know we get 0. Likewise, if we do E with F, we don't need to do F with E because we can use skew symmetry. So really there's only 3 things to do. So let's calculate first maybe H with E. So notice that'll be HE minus EH. So that's 1, 0, 0 minus 1 times 0, 1, 0, 0 minus 0, 1, 0, 0, and then 1, 0, 0 minus 1. Okay, so I'm claiming that this algebra is going to be closed under this operation. So this should be a linear combination of things from E, F, and H. So we should try to write it that way. And of course, like I've chosen this basis so that this multiplication happens like kind of as nicely as possible. So let's do this matrix multiplication right here. And we'll notice that we get, let's see, we get a 0 for this entry just by doing our little swivel operation for matrix multiplication. We get a 1 for this entry for the same reason. And then we get 2 zeros down here. And then likewise here, we'll get the same thing but with the signs reversed. But let's notice that this will double up. So the minus signs cancel, and we're left with a 2 in this entry, but that's exactly equal to 2e. So that's our like bracket relation of h with e. So if we do h with e, we get 2e. So maybe we could like erase all of this and then write down here that we get 2e. So in some ways you can think like we have some sort of eigenvector eigenvalue relationship where we do this left bracket with h on e and we get a multiple of e. So that's actually really, really important. And that makes this vector right here seem like a really important vector because it has kind of this eigenvalue, eigenvector type operation when you multiply by the left, which is really bracketing from the left. And then maybe like similarly, we can calculate h with f and we'll get minus 2f. So that really lends motivation to the importance of this vector h even more. is that it decomposes, or that it has this eigenvector eigenvalue relationship with the F vector as well. Okay, so let's see. We got one more to do, and that would be E with F. And if we do E with F, we'll actually get H. And so you can check that again by just doing the commutativity rules again. So in some ways you want to think about this SL2 as, you know, maybe let's put a 2 here, a 0 here, and a negative 2 here as this like string of vectors. So maybe up here in the middle, and then in the middle here. So we've got E up here, H, F down here. And if you combine anything from these two spots, kind of their, you know, their weights, if you will add together. And so you know you'll be one of the multiples of this kind of weight space. So notice if we combine H with F, then we stay down here at negative 2 because 0 plus negative 2 is 0, right? If you combine E with F, well then their weights add and you get something with H, right? If you combine E with H, well they add to 2. But then if you were to do something like combine E with itself, well, you would get 4. 2 plus 2 is 4, right? But that's outside of, there's nothing of weight 4 here, right? So there's this nice kind of like geometric string structure to our SL2. Okay, so, and why is this so important? Well, like most Lie algebras can be decomposed using this SL2. Like SL2 lives inside of almost every other Lie algebra and can be used to break it into parts. So if you understand, well, more than this, but you really need to understand the representation theory of SL2, then you can understand all of the Lie algebras. Furthermore, if you notice, this thing is three-dimensional, right? And in fact, if you were to do a change of basis, you could see that this is the same as C3 with the cross product. It's the same structure. So this bracketing operation with E, F, and H, you know, if we do a change of basis, you'll get something similar to cross product operation with three-dimensional complex vectors. And I mean, that's not like super clear, but it's not super hard to check either. And it really motivates this thing that I said a little bit earlier, which was like most Lie algebras can be represented as matrix Lie algebras, and that should include cross product as well. So cross product can, and it looks like this. Now I've worked over C here because if you work over R, something a little bit different is happening and they're not exactly the same. You need something else. But since we worked over C, we're okay. Okay, so let's look at maybe the most important infinite dimensional Lie algebra, maybe to finish things off, which I think will be like, okay, so so this example like requires a little bit extra. So maybe let's title this the simplest infinite dimensional Lie algebra. You know, obviously there's probably a simpler one, which would be just the trivial one where the bracket is always 0, but that's not super interesting. So this would be maybe the simplest one where the bracket isn't always 0. So what we need here is like an action space. So a space for things to act on first before we can actually define the vector space. So let's look at this. So remember our polynomial algebra from before? Well, we could have a polynomial algebra with, instead of one variable, infinitely many variables. So we have x0, x1, x2, so on and so forth. So there we got polynomials. with infinitely many variables. So maybe we would write these as P, and then I'll just put like X arrow to say that it has those infinitely many variables. Okay, then our Lie algebra will not be this space with additional structure. It'll be a space of linear transformations on this space. And so let's define like linear transformations on this space, and we're going to define an infinite family of linear transformations. And so first of all, if we have n not equal to 0, so n is an integer here, but it's not equal to 0. I guess I should say like n is a positive integer here, but it's not equal to 0. Maybe we'd say n is a natural number. Although I guess in Europe, the natural numbers have 0 in them, right?
I've had this argument with so many of my students about whether or not to include 0.
My comments are always like mega about natural numbers like containing. I just feed into it. I don't really care one way or the other.
I think it's a good lesson in it's whatever you say it is as long as you define your notation. So if you say n means this or whatever, or n without 0, as long as you're clear, I think it can be whatever you want it to be.
Yeah, exactly. Okay, so for n not equal to 0, let's define, I'm going to call it alpha minus n. So this is going to be a linear transformation from, let's maybe call this vector space V. So it'll go from V to V. And what does it do? Well, you know, I've named it like kind of crazy, alpha minus n, but that's just really for it to like kind of hold up for notation if you were to like look at the definition presented somewhere else. But what it does is it takes a polynomial, so I'll call that polynomial px, and all it does is it multiplies it by xn. So this will be xn px. That's all. So that's a linear transformation. We can just multiply by a variable. So I mean, very trivially, we could do an example here. So alpha minus n on x1 squared, alpha minus 3 on x1 squared minus 2. So that'll be x3 x1 squared minus 2x3, right? There. So you just multiply by one of the variables. Okay, so that's this negative linear transformation, this negative subscript here. And then actually, no, I think this is fine. And then let's say, what about for positive ones? So for positive ones, so again, that's going to be a linear transformation from V to V. And what it will do, so alpha n on px here, it will essentially be the derivative with respect to this variable. So let's see how we would write that. We could write this as n times the derivative with respect to xn of px. So we could define it like that. So here we could do another example. Let's say we do alpha 2 acted on x2 squared plus x1 x2 plus x1 cubed. So, well, first off, we need to multiply by 2. And then after multiplying by 2, we need to take the derivative. So if we take the derivative of this with respect to x2, we'll get 2x2. But if we multiply by 2, we'll get another 2. So we'll get 4x2. So that's like that term. Then if we take the derivative of that, well, the x2 is going to disappear. So we'll get 2x1 because we have to multiply by 2. Then if we take the derivative of that, well, that doesn't depend on x2, so we get 0. Okay, so that's going to be for n not equal to 0, but what about for n equal to 0? Well, we'll do like the most boring thing possible, and that is we'll say alpha 0 on px is just 0. So it just kills it. Now, I guess that could be written as one of these, right? Because it would be just 0 times the derivative, but that would just give you 0. Okay, so now that we have this, we'll define the following. So let's set, I'll call it H, maybe this like calligraphic H, to be equal to the span of all of these alphas. So we've got what, like alpha minus 3, alpha minus 2, alpha minus 1, alpha 0, alpha 1, alpha 2, ... So there we've got an infinite dimensional vector space, right? Because we're taking linear combination of infinitely many different things. And now, well, we would probably need to see what the bracket is, right? Oh yeah, and then maybe we should say, what is this? Does this have a name? And it does. This is called, well, there is no like the Heisenberg-Lie algebra, but this is a Heisenberg-Lie algebra. Because a Heisenberg-Lie algebra is a Lie algebra with certain properties. And so this has some of this has the properties that turns it into a Heisenberg-Lie algebra. Okay, so let's maybe check the commutation relation of these types of things, and then I think we'll be good. So let's maybe do, for example, alpha m with alpha n. Okay, so let's break this down into a couple of cases. Well, let's notice that if both positive or negative, or one of them is 0, or 1 equals 0, then this thing equals 0, right? I mean, so that's like not too hard to check. We could do it like by an example, like for like C work. So like alpha 2, maybe like alpha minus 3, alpha minus 2 on px. Well, that's going to be the same thing as doing x3, x2 minus x2, x3 on px, right? So we'll get 0. And then likewise, if we do them both positive, we'll also get 0 because, well, polynomials satisfy the rule that you can change the order of partials and you're okay, right? Yeah. So that means the only interesting case is when one is positive and one is negative. So let's maybe look at this. So alpha n, alpha minus n. Now I'll maybe leave as a homework exercise that this is the only time that you get something that's non-zero, but let's work this out to see what happens. So in order to know what it does, we need to know what it does to a polynomial. So let's see. This is going to be alpha n, alpha minus n on the polynomial, and then minus alpha n, alpha minus n, alpha minus n, alpha n on the polynomial. Okay, well, let's just work from inside to outside, which is what we should do because these are like linear transformations. So this is going to be alpha n operated on xn times the polynomial. So that's what this turns into. And then this is going to be alpha minus n times n, and then the derivative of the polynomial with respect to xn, right? That's what this alpha n does. I guess I should say here n is bigger than 1 or equal to 1. Okay, but let's recall that this alpha n will mean take the derivative and multiply by n. So let's do that. And then this says multiply by xn. But if we take the derivative of this with respect to xn, we have to use the product rule. So if we do the product rule here, we'll get n, and then we'll have p of x plus, let's see, xn partial p with respect to xn. So that's what we get for the product rule here. And then if we do the same kind of thing over here, well, we don't have the product rule anymore. We just have multiplication. So this is minus n xn partial p with respect to xn. But if we notice some stuff cancels, this guy cancels with this guy, and we get n times the original polynomial, which we can really view that as n times the identity linear transformation, right? Because it didn't change the polynomial. So this happens if one is positive and one is negative, and they're equal and opposite, but it's pretty easy to check that this is the only time that you get something that's non-zero. So maybe we could summarize this as follows. So so as a vector space, it's going to be these sorts of linear combinations of these sorts of elements, and then with the following bracket relations. So we've got alpha m, alpha n is equal to m, but only if m and n are equal and opposite. So in other words, delta m plus n 0. So in other words, this is m if m equals minus n and 0 otherwise. So what we have is that most of the time, these two operators commute, right? Because most of the time, they don't add to 0, right? But every once in a while, they do add to 0. And I think like from a physical interpretation, you can interpret these as like creation and annihilation operators, right? Yeah. So like the multiplication, I mean, now I'm really talking like out of my breadth here. But like the multiplication by the xn is like creating a particle of like energy n. And then the derivation is like removing the particle of that energy or something. Okay, so I think that's like all I really wanted to say.
No, it's fascinating. I love this final result because I can immediately see how closely it relates to what we're going to do with commutators and the Heisenberg uncertainty principle. No, I didn't know there was such a thing as a Heisenberg-Lie algebra, but I can now see, as you were going through, I was sort of thinking to myself, where is the point where this is going to link to what we're going to do next? And then it came there right at the end with that delta appearing. That's exactly, yeah. It's where we're going. Brilliant, right. So I guess, given all of this perfect preparation for part 2, we should jump over to my channel and do some quantum physics.